Alright, so this is a continuation of lesson 5.6, graphing inequalities with two variables. But before we really get into graphing the two inequalities and all the options we have for the solutions, we're going to quickly review, well, what if there was just one variable? And so when we have the inequality y is greater than 4, if we need to graph that, we want to treat it as y equals 4. And way back in November, we learned what this meant if you just had a y equal to a number. Well, where y equals 4 is right here. But a line that is y equals 4 means that every point on that line has a y value of 4. So that point, that point, that point, that point, that point, and then to the left, to the left, to the left, and on and on. I could go forever to the left and forever to the right. Now when I connect these points, I still go back to, well, what's my inequality sign? If it's just greater than, remember that means dashed. So when I connect these points, I'm just doing it with a dashed line. And then if it's y is greater than 4, think about where that is on the graph. It's all the area that is above 4. So that is the section that is the solution to my graph, because 5 would be greater than 4, 6 would be greater than 4, 10 would be greater than 4. Anything above 4 on the graph is greater than 4. Now x is greater than or equal to 3. We treat that as x equals 3. X equals 3 is right here. That's where x is 3 on my x-axis. And then all the other points that would have an x value of 3 are up and down from that. Now because the inequality symbol is greater than or equal to, well, now what we're doing is we are making a solid line. And where are all the x values that are greater than or equal to 3? Well, those are all the ones that are to the right of 3. That's where the x values are getting bigger on the x-axis. Okay? And now the last one, y is less than negative 2. We treat it as y equals negative 2. We go down to negative 2 on our y-axis. Every point that has a y value of negative 2, I go forever to the right, forever to the left. Because my inequality symbol is only less than, that means I'm going to make it a dashed line. And x or y is less than negative 2, where those are all the values that are below negative 2. Now, if we had more of a window in our graph, we would just shade as much of below the line as we can. But since my window ends right here, I only shade between the line itself and where my window ends. Alright, from the first video of 5.6, we saw what steps are necessary to solve a system of inequalities by graphing. And so we're going to review those for the next couple of examples and learn how to graph it and then also where to shade for our solutions. So the first thing is when we look at this inequality, remember we're actually treating it as if it were an equal sign in y equals mx plus b form. That's going to make it easier to plot this on our graph. So I see that I have a y-intercept of 1, so that goes right here. And if my my slope is 3, that means up 3, right 1. I'm out of room, so I can also go down 3, left 1, down 3, left 1. Now when I look at my inequality symbol, if it's only less than, that means what? That means dashed. So after I graph my points, I have to determine, am I connecting them with a solid line or a dashed line? Well, this is an example of a dashed, like that. And the next thing I need to do is is test a point. Well, 0, 0 is not on the line. It's super close, but it's not. And because it's not, I can still use it to test. So from this inequality right here, I'm going to make the x 0, and I'm going to make the y 0 and see if it makes it true. So is 0 less than 3 times 0 plus 1? Well, that would be 0 is less than 0 plus 1. 0 is less than 1. Check. That works. Because 0, 0 worked, that is a true statement. That means I'm going to shade the region of the graph that includes 0, 0. So I'm shading below the line because 0, 0 worked and it's below the line. So I'm shading everything below the line. So I shade all of that. And if you want to go all the way, get every single square inch, there you go. Any region in that highlighted area would make this inequality true. So let's go right next door. We're going to go to number 9. And I'll keep my rules right here so we can follow those. And I'm going to treat this as y equals negative x plus 1. Because now I look at that and I say, okay, y-intercept at 1, a slope of negative x. Well, that means negative 1x or negative 1. My slope is negative 1. So down 1, right 1, down 1, right 1, and I keep going, keep going, keep going. Or I can go the other direction, up 1, left 1, up 1, left 1. I look at what my inequality symbol was. It was greater than or equal to. So if it's greater than or equal to, that means it's going to be a solid line. So I connect these points, and you'll want to use a ruler. I don't want to use a ruler because it forces me to kind of turn my paper during the video, and that's not very fun for your eyes. So now, again, I noticed that I need to test a point, and 0, 0 is not on the line, so that makes it easy to test. And I'm going to plug in 0 for y, and I'm going to plug in 0 for x, and see if it makes it true. So 0 greater than or equal to, this negative sign is still there, and I replace the x with 0, and then I have plus 1. So now I have 0 greater than or equal to, well, negative 0 plus 1 is just 1. Is 0 greater than or equal to 1? No, it's not. That is false. So that means the region of the graph that included 0, 0 doesn't work. So I'm shading the other region of the graph, which is everything that's going to be above the line. So I shade all this right there. Fantastic. So we graph the points, and then go back and either connect them with a solid or a dashed line. Then we test any point that we want. We can choose any point, not on the line. But 0, 0 is the easiest number to work with. And then, based on the results of the testing of the point, I can determine, am I shading above the line or below the line? As we get to number 10, you'll notice that equation is not in y equals mx plus b. This one is in standard form. And when we have an equation or an inequality in standard form, the way we graph it is by finding the intercepts. And you find the x-intercept by making the y value 0, and we find the y-intercept by making the x value 0. Now, just like we did up above when we turned these equations quickly just into y equals form for graphing purposes, we're going to do that as well here. So when I make the y 0, notice that x equals negative 3. That's my x-intercept, which is at the point negative 3, 0. And when I change my x into 0 to find my y-intercept, y equals negative 3, and that's the point 0, negative 3. So these 2 points right here are my step 1. I'm able to graph 2 points that are on this line, or in this case, our inequality. So we're at negative 3, 0 for our x-intercept, 0, negative 3 for our y-intercept. Now from those 2 points, I still need to connect them for step 2 with either a solid or dashed line. Well, look at your inequality. It was greater than or equal to, therefore it is a solid line. Solid line. And we're going to be right here for our solid line. Now I'm at step 3. I can test 0, 0 because it's not on the line. And I'll do that quickly right down here with this little space that we have. From our original inequality up here, I'm making x 0, and I'm making y 0, and I'm trying to determine, is that greater than or equal to negative 3? Well, that just becomes 0 greater than or equal to negative 3, and yes, 0 is greater than or equal to negative 3. So check, because it's true. So I shade the section of the graph that includes 0, 0. I do all this. Any single point in this entire shaded highlighted region would make the original inequality true, so they all qualify as solutions to the system of inequalities. Okay, go ahead and pause and write the rest of that down if you need it before we move on to the next one. So as we look at number 11, again it's in standard form. So to find my x-intercept, I make the y value from the inequality 0, but I also treat it as an equation because that's going to help us with graphing. So as I solve this out for the x equals 2, which makes my x-intercept point 2, 0. So that point goes right there. And then for the y-intercept, we make the x value 0, and this results in an equation of negative y equals 2. Well, I don't want to know what negative y is, I want to know what positive y is. So if I divide both sides by negative 1, this side turns into a positive y, changes the sign, and the other side changes signs as well, so you get y equals negative 2, or a y-intercept at 0, negative 2. And then we have that point. Based on our original inequality, which was only less than, there was no equal to part, that means it's going to be a dashed line between these 2 points, or that goes through these 2 points. And now I'm going to test, again, 0, 0. And you can see on almost every graph that we do for these, we can test 0, 0, which makes our lives easier. So we plug in 0, 0 into the original inequality. So I make the x 0, I make the y 0, and is it less than 2? Well, 0 minus 0 is 0. Is 0 less than 2? Yes, it is. That's a true statement. So my solutions, all the possible points that make this inequality true, are where the region of the graph where 0, 0 does occur because it was true. So that means everything above the line, works. So all that area are the solutions to this system of inequalities. Alright, we got 2 left. Again, we're in standard form. So to find my x-intercept, I make the y value 0 right here. And follow the math. 2 times 0 is 0, so x equals 4. That gives me the x-intercept at 4, 0. That's that point right there. And then when I find my y-intercept, I make the x value 0. 2y equals 4. We'll divide by 2 on each side. Y equals 2. That gives me the y-intercept of 0, 2, which is that point right there. Based on my original inequality symbol, which was only less than, did not include the equal part, that lets me know that this is going to be a dashed line. And we're going to be approximately right there. And now I'm going to test 0, 0, because again, it's not on the line, which allows me to test it. And I'm plugging 0, 0 back into the original inequality. So I have 0 plus 2 times 0, and I'm trying to see if all that is less than 4. Well, that means 0 plus 0 less than 4. That gives me 0 less than 4, which of course is true. That means the region of the graph that does include 0, 0, because it was a true solution to the inequality, then my solution is all of this region right here. Any point in that region would make the original inequality true. Alright, last example. Are you sad? It's almost over. Oh no. So when I do this, standard form again, I make the y0 to find the x-intercept. 3 times 0 just disappears, so I'm left with negative 2x equals 6 divided by negative 2 on each side. X is negative 3. That's the point negative 3, 0, which occurs right here. To find my y-intercept, make the x value 0. These disappear. 3y equals 6. Divide by 3 on both sides, y equals 2, which is the y-intercept at 0, 2. And now, because of my original inequality symbol, it included the equal then, so this is a solid line. We're right about there. And now I need to test 0, 0. When I plug the 0 in for the x and y, you see it results in a false statement. So where 0, 0 was, I do not shade the region of the graph where that was. I shade the entire other region of the graph, which in this case is above the line. Alright, so now you'll go ahead and do all the practice problems in the homework and do your best. See you next time.